PhD student here at the University of Minnesota Twin Cities in the AEM department. And a lot of my work is all about launch vehicle control design on a quadcopter test bed. So with the renewed interest to send payload and crew to the moon and eventually onto Mars, mission objectives are going to become more complex. And so the technologies on the different vehicles that complete those objectives are going to need to become more advanced. Specifically, what I work with are the flight controllers or the autopilots for your launch vehicle during ascent, as well as your landing system during descent to and ascent from the moon. These are going to need to become more advanced in order to complete these more complex mission objectives. So a survey done in 2002 showed that between 1990 and 2002, 41% of all failures in subsystems in launch vehicle launches could have been mitigated had an advanced guidance, navigation, and control technology been used. 41% is a very large number, but then again, 2002 is a long time ago. So why don't we kind of fast forward and look at a more recent example. So when I actually found this, it was a couple days after this launch happened, but in August of last year, Astra, a launch vehicle provider, their LV0006 launch suffered a launch failure due to the engine malfunctioning from a propellant leak and ignition. And in this video, the vehicle goes up and kind of starts to just kind of take itself away. And that's because the improved guidance, navigation, and control software on board was able to recognize that there was a problem and adjust its course. And everyone was very happy with their GNC algorithm. So when the executive VP and chief engineer is complimenting the work that you do, you should keep doing it. So advanced GNC, I specifically, GNC as a whole, there's a lot of stuff that goes into it. What I'm going to be talking about is the control side of it. So what actually is guiding the rocket. So I hope I've convinced you that it's like, oh yeah, we need to be using advanced GNC algorithms or technologies on our launch vehicles. Why don't we always use it? Well, that's because launch vehicles are very expensive. And when you test something on them or when you implement something on them, they need to work the first time and every time. And a good way to measure how ready a flight controller or any technology is to fly is using NASA's metric called technology readiness levels. So this is just a guide that NASA uses that you can to help determine how mature a technology is, 9 being ready to fly on the launch vehicle. And it's a treacherous path to go from 1 to 9, particularly for launch vehicles, because in these middle TRLs 4 through 6, you need to have what's known as a relevant environment. You need to have test experimental data on a relevant environment. Well, for launch vehicles, that's really hard to replicate. The dynamics with a launch vehicle, how expensive they are, it's hard to replicate that kind of environment. And so there's not a lot of test beds and testing environments to test these controllers on. Once you get up into the TRL 7 through 9, there's a bunch of different things from some crazy stuff they did on an FA-18 jet, as well as some vertical takeoff and landing systems. But you want something much lower cost and lower risk to kind of help move these technologies to higher TRLs. There has been some work done at NASA Langley in this space and creating these test beds, and we're looking to help supplement that and add to it. So the test bed that I'm working on, what does it look like? Or, well, before I get to that, our objective is to create a test bed that is considered a relevant environment for testing new launch vehicle control systems at significantly lower costs and risks than previous test platforms. So those vertical takeoff and landing ones and the FA-18 jet. And what this will do is it'll reduce the time that new flight controllers are in those TRLs 4 through 6. It'll reduce the cost and risk of testing new flight controllers in those systems, which will help just move them higher up into the higher TRLs. And then because that process from going to TRL 1 to TRL 9 is going to become a lot easier, we can start testing more advanced and maturing more advanced flight controllers and actually having them be proven on real flights. So what does this test bed look like? Well, it looks like a quadrotor helicopter with a flexible inverted pendulum and a hanging pendulum. And so basically you can imagine the quadcopters balancing this inverted pendulum like a pool cue on your hand. And there's also another pendulum hanging from it that's kind of trying to disturb it and kind of mess with it. And what this does is it, at a very low level, or very high level, I should say, captures the dynamics that these autopilots for the launch vehicles have to capture during launch. So there's a whole bunch of stuff going on with a launch vehicle. We're not trying to create it one-to-one, just that surface level. And I guess what do those dynamics on a launch vehicle look like? Well, first you have your launch vehicle control allocation. So the way launch vehicles controls, you have your overall thrust, and then you're able to gimbal, you're able to kind of point that thrust vector. So you're able to control your thrust and then kind of your attitude or your torque. And that's exactly how a quadrotor flies. You have your overall thrust, and then you can adjust the speed of the propellers to kind of pitch, roll, and yaw. The aerodynamic instability of a launch vehicle. So as launch vehicles are going up, they have all this wind kind of that they're pushing through. And if you take all of the pressure of the wind that's hitting the side of the launch vehicle and bring it down into one point, you can have it, that's known as the aerodynamic side force. And it's acting on the center of pressure. So if you take all of that wind and it can be shrunk to that one line. And if your center of pressure is above your center of mass, all bodies want to rotate about their center of mass. If your center of pressure is above it, it's going to want to cause the launch vehicle to tip over on itself. So a launch vehicle, as it's pushing through the atmosphere, actually wants to tumble over on itself. And we are attempting to replicate that using the gravitational instability of the inverted pendulum. So the inverted pendulum, just for the quadrotor, hovering in place is not going to be taking off like a launch vehicle, just hovering in place. The inverted pendulum is going to want to fall over due to gravity pulling down on it. And so that's how we're attempting to replicate the aerodynamic side force effects. So a launch vehicle, because they're super tall and there's a lot of thrust going on and there's a lot of forces acting on them, they actually flex, they bend while they're going up. And that's something that the flight controller actually has to account for. And in order to replicate that in our test bed, we make a really bendy, really flexible pendulum that wobbles around. And that our quadcopter is going to have to account for. And then lastly, we have our slosh disturbances. So on launch vehicles, they have big tanks of fuel, and as it's going up, the slosh can move around and cause the flight controller, or cause it to kind of tip over on itself. And the flight controller has to be aware that it's not going to cause it to go unstable and fall over on itself. And so we're just assuming one tank instead of two tanks. A lot of launch vehicles have two tanks for your fuel and your oxidizer. We're just assuming one tank. And in order to replicate that, we have our hanging pendulum that is just going to kind of try to replicate those dynamics of just getting in the way of what the quadcopter wants to do. So that's what our test bed looks like. I'm now going to kind of talk through the two parallel paths that I've been working on in this project. You have the theory side, which is all the math and the MATLAB code that goes into that you need to know before you can start actually flying something. And then there's the hardware side. How do you actually, once you get all of your MATLAB code running, how do you get an actual test bed flying? So for the remainder of this presentation, I'm going to talk through the theory that I've worked on. Right after this presentation, one of the exhibits will show the hardware that was designed last summer for this project. But I know theory kind of sounds boring. I think it's pretty cool, so I hope you'll stick with me. Oh my gosh, equations. Don't worry, I'm not going to talk through these. I'm just going to show you that I've done my homework and that the first step is formulating your simulation. So you have your computer, you want to replicate your system on your computer so that you can test stuff on the computer before you put it on your quadcopter. So you do some math, you get your equations of motion, the equations of motion for a launch vehicle and the equations of motion for the test bed. These just describe how how everything moves with time. So once you get your dynamic simulations and you get these equations of motion describing how these bodies move, we want to compare these bodies. I haven't gone too rigorously into the comparison between these bodies, but what I have done is if you've taken a controls class, there's some more math that you can do to those equations that I just showed, and you'll get something that are known as poles. And this diagram, controls engineers can look at this diagram and recognize, oh, the system's going to respond in this way. Like I can look at that and say, okay, this is how it's going to kind of be. This is unstable. Like, but the point that I want to get across to you is the black X's are the launch vehicle's poles. This is how the launch vehicle reacts. This is how it moves. And we wanted to get the red X's to line up with those black X's. And the way we did that is by adjusting the parameters of the test bed. So adjusting the length of the pendulum, adjusting the mass of the pendulums, adjusting those parameters until we get those X's to lie on top of each other. And you can see after I did a lot of fiddling around with the parameters that the red X's lie on top of the black X's, mostly. There are two extra X's right on top of each other at 0. That's just because we have the quadcopter modeled as an extra body, was the engine we're just assuming is kind of part of the vehicle. And then the slosh poles don't perfectly line up, and that's just because of this has some damping and there's no damping here. There's a dissipation in energy here and there's not there. But from a very high level, by adjusting these parameters, we were able to see that the responses of these dynamics could align. Again, there's a lot more rigorous work that can go into comparing launch vehicle and test bed dynamics, such as using your pi groups, dimensionless parameters. But from a high level, this is what I did to compare the dynamics so far. So the next bullet is synthesizing baseline controllers. So these are all controllers that have known properties. They're used very frequently. These are things from, like, if you're familiar with controls, proportional integral derivative controllers, linear quadratic regulators. I'm not going to go into details into this. I'm actually going to talk more on the purple bullet, but I did want to acknowledge that I am just kind of skipping over that one, and I'll talk a little bit more about that at the end. But the purpose behind this green bullet is we just want to implement an autopilot that has a lot of history behind it. People have studied rigorously, and when we get this to fly, we know how it'll behave. So then now I'm going to move on to the purple one and kind of the cool stuff that I'd like to talk about, and that's synthesizing novel algorithms. So I would like to assume that most of you have seen the SpaceX booster landings. If you're not, I highly recommend you look up SpaceX booster landings and watch those because they don't look real. But these algorithms have a really hard time flying on real systems. There's only been like one group that's actually done this. And that's because they're hard to validate and say, yeah, let's put them on our billions of dollars rocket. So a test bed like this can really help those kind of algorithms, these trajectory optimizations where they touch down softly, excel to being more frequently used. So for the next couple slides, I'm going to just talk about trajectory optimization, like what's going on here, and then I'm going to connect it, trajectory optimization from a super high level, and then connect it back to the booster landing problem. And then I'll show you some results that I did with my simulation. So let's say I'm in my apartment at A and I need to get to Ackerman Hall to give a presentation at B. I want to make sure that I get as close to the room that I am presenting in as possible. So I want to minimize my error. I don't want to end up in the wrong room. So my goal is at B goal, and I want to minimize the error from where I end up. So that's going to be some equation. We can use some calculus in order to figure out the best path from A to B. And that's great. I mean, we would all assume that it's going to be a straight line. Shortest path between 2 points is a straight line. But when we add the dynamics, let's say I'm walking or I'm on foot, I'm not riding my bike, I'm not driving. We have to add a constraint that I'm on foot. So that can change the trajectory based on like those equations that I showed for like the test bed. Like if I'm walking, the path is going to change. And that also might affect your error. We would hope it wouldn't. I don't think that would affect me getting to the right room, but it might affect the error. Then we also want to add another constraint. I was informed that I had to enter the building through the bayless atrium, so I can only approach the building from a certain angle. So that limits where my path can take me. So you can see this is our previous path, this dotted line. And that doesn't satisfy our cone. We want to get within those two blue lines. So once we add that constraint as well as our dynamics, it's going to update our path and it might change our error again. And then let's say I don't want to get sweaty before I get here. So I have to have some sort of velocity constraint. So I'm not moving too fast. So I had that velocity constraint, so I'm not moving too fast. And that can, again, change my trajectory and my error. Again, this is all just using math in order to figure out the optimal trajectory. These are all going to be equations that we figure out, but I didn't want to, on a Saturday morning or afternoon, I didn't want to present too many equations. So what we can do is you can keep adding up all of those constraints. You can keep adding more and more if you want, and we can just lump those into constraints. So you have your objective where we're trying to minimize my location error subject to all of those constraints. And what we can do is we can take, after we run the program and it gives us our best trajectory, whatever it may be, we can say that error, whatever this is our best error. That is as close as we can get to our final destination. In this case, it's probably going to be 0 because all of my constraints shouldn't prevent me from getting to the right room. But I just wanted to have the difference so we can visualize the best error. So we take that best error now and we set that as our new goal, because we know based on everything we've said so far that we can't get any closer to our destination. So then we go through the whole thing again, you now setting B goal as our new goal. And now instead of minimizing error, we're minimizing our fuel. Or in this case, if I haven't eaten breakfast yet, I want to make sure I don't faint before I get to my presentation. So I want to minimize my fuel. I know it's kind of a stretch, but I'm going to connect it to launch vehicles in a moment. We want to minimize our fuel. So we go through the first one, minimize our error, then we take that new location and use that to minimize our fuel. And that'll give us this orange trajectory. And then the final step that we do is I can guess that it takes me no more than 60 minutes to walk here, right? So I'll start my simulation assuming that I'll get here in 60 minutes and I'll run it and it'll give me a solution. And I'll say, oh, well, maybe I can get there in 59 minutes. So then I'll decrease the time and I'll run it again. And I'll keep doing that and decreasing the time until the computer, like let's say at 14 minutes, it gives me a result. It'll take me 14 minutes to get here, given all of my constraints and everything. And then at 13 minutes, the computer says, I can't find a solution to that. That means that I know that I can get to my destination with the least amount of error, with the least amount of fuel in 14 minutes, no less time. So now I've optimized over my error, my fuel, and my time. And that's the algorithm that I implemented for the booster landing algorithm. You go through, you find, our goal is to, instead of this walking example, we're trying to softly land this, the simulation of this test bed using this trajectory generation algorithm for the minimum fuel booster soft landing problem. So if we have our initial position and velocity of our launch vehicle, kind of like where I'm starting in my apartment, and we want to get down to our launch pad, we want to minimize our error. then we want to minimize our fuel, and then we want to kind of grid over all of the possible times to find the minimum amount of time. And there's a lot of other constraints like control constraints that I'll explain in a second that didn't apply to my walking example, but it's the same kind of idea. So what are some of these extra constraints, or what are the constraints that we are actually implementing in the booster soft landing problem? Well, the approach angle one is pretty similar. You have to, for these launch vehicles, you want to make sure that they don't approach in like horizontally. You want to make sure that they come in within some cone, so they're kind of coming in as vertically as possible. And that's just so that they're not taking some weird trajectory sideways. And so that's kind of our approach angle constraint. Then we have our upper bound on our velocity. So like I didn't want to run. We don't want these launch vehicles to exceed a certain velocity because of all of the aerodynamic stresses on the vehicle. You don't want them to ruin the vehicle. You also don't want your vehicle to come screaming into the landing point and until the last second. So you have a maximum velocity constraint. And then you have some extra control constraints that I didn't have in my walking example. So these boosters, they have some thrust being generated by their rocket engines. We can model that thrust vector as this blue thrust. The first constraint on the thrust is there's a maximum thrust. There's only so much thrust you can generate with your rocket engine. So you have an upper limit on your thrust. And then these rocket engines actually also have a lower limit on the thrust. Due to the way the chemistry works, the flame, you won't produce any thrust because there won't be any flame below a certain thrust threshold. You can't just go from 0 to whatever you want. So there is a minimum thrust before your flame dies and you would have to reignite your engine. So there's a minimum thrust magnitude. And then lastly, a lot of these vehicles, not just launch vehicles, but this algorithm can also be used on other systems. They need to be pointing down. They might have some sort of navigation system that's looking at the ground and recognizing, oh, there's the pad. There's like a camera pointing down. So a lot of times they have to have a constraint where they're pointing within some angle of the ground. They can't like turn upside down. They need to be pointing downward. So that's our last constraint is, in this case, I have the angle is 90 degrees. It's much less than that in reality, but I just wanted to make it clear that like your thrust angle where this blue arrow is pointing has to be below this green theta max. So using all of this, using all of these constraints for the booster soft landing algorithm, I replaced the dynamics of a booster with a simplified dynamic model for our test bed. So I ran this algorithm for our test bed. That's this trajectory generation algorithm. I ran it. I gave it our initial conditions, our initial positions and velocities, gave it our trajectory generation algorithm, and it spits out, follow this trajectory in time and space. Like be here at this time, be here at this time, be here at this time. And then what we do, kind of returning to the thing that I skipped earlier in the presentation, is I give that trajectory to one of those baseline controllers. So in this case, I'm using a linear quadratic regulator. Don't worry about exactly what that is, but it's just a controller that we have known properties about that I tune so that I give it this trajectory and the test bed's going to follow it. And then out of that controller, it goes into the test bed dynamics and it just keeps following that trajectory. So here are some results. On the left is the result of just the trajectory generation. So just this block. So the purple one is the minimum landing error. That's that first run. How close can we get to our point? It just minimizes that landing error. And you can see, so if this gray grid is our like our approach constraint, that angle that we have to approach from. So our line can never go below this. And then the brown is the ground. It actually just slides against, it follows that constraint very closely. I should do this on the computer so people on Zoom can see. But it actually follows this grid until it goes to our landing point. So that's the trajectory. I figure out where that ending point of that purple is, and then I give that to the run 2, where we then find our minimum fuel, and the computer says that you actually want to just launch from your starting point and kind of just turn off your thrusters for the duration. You kind of want to just go up really high and then just kind of wait and just at the very last second turn on your engine and land. So instead of following this, it actually goes way up high and then comes down and softly lands after the second run. So once I got this trajectory from that algorithm, I then gave it to my controller to then follow. So if we take this 3-dimensional plot of our trajectory, this green, and we turn it into 2D plots versus time. So we have this x-axis, that's this dashed red line here. If we have our green along our y-axis, is this dashed red line here. You can see it's very small because everything is kind of in the plane. Oh yeah, I did not mention that the starting position is 4 meters off of the ground and 1 meter to in the x direction from our origin. And then the altitude is this dashed red line. It goes up and then comes down. And then the blue is what actually the quadcopter, when I gave it the trajectory, what the quadcopter was actually able to follow. So the blue is, it doesn't follow it perfectly, and that is because it's also trying to balance the inverted pendulum at the same time as following this trajectory. And I mean, this looks really cool on, I think it looks cool on 2D, but it would be a lot cooler if we had like an animation that showed like what's actually going on while the quadcopter is flying around and following this trajectory. So I do have a simulation here of an animation of the simulation of the quadcopter following this trajectory. So the dashed black line is that green line, that is our optimal path that we are trying to follow. This little red cross is our quadcopter. There is an inverted pendulum on it that I think you can see in this figure. There is no hanging pendulum. I did not include it in this simulation, but the quadcopter is balancing the inverted pendulum. And then you'll see as it traces as the quadcopter moves, there will be a green path that is being traced by the quadcopter as it moves. On the left here is as though we are looking as though we are just like fixed and just watching it from like a corner of a room. Whereas the one on the right is as though it's a camera following the quadcopter. I'm just gonna play. You can see it goes up, kind of turns off, or well, it doesn't turn off because we have that minimum thrust constraint. So the thrust turns way down and then it goes up and then falls. And then at the last second, it turns on and catches itself. And you can see it does it doesn't follow the dashed black perfectly. And that's because you can see kind of moving to catch the inverted pendulum. And then it comes and it's the altitude requirement to land. So that's kind of what we've done with the theory. We want to take the dynamic modeling that we did, compare it to the launch vehicle dynamics, run some baseline controllers, and then develop a novel control algorithm. And I mean, that's great, Liam, but that's just a video and that's just a simulation. We want to actually see, get something flying. And that's when I encourage you to go and see our booth downstairs, where we actually have the quadcopter set up. So in this first bullet, we just had to design and build the hardware, which is downstairs. It is not flying because we're at the point where we're trying to get it flying. Then we have developed supporting software for it, and we are currently in the process of tuning things and getting things flying so that that simulation I just showed can someday be reality, and we can have a quadcopter flying around testing out booster soft landing algorithms. So with that, thank you all for your attention. I hope I didn't put you to sleep too much, and I'm willing to take questions.
So I was noticing on your velocity curve, you have a really wild spike in there. What caused that?
Here?
Yeah.
Yeah, so that is going to be because as the pendulum starts falling over, the quadcopter is going to correct and catch it. So I think in that moment,
So it pulls back and then it resumes its course.
yeah, so I think that's gonna be right after the hump. You can see it kind of really quickly goes over to catch it. So it sees that the inverted pendulum is falling over, so the quadcopter speeds up to the other side to catch the inverted pendulum from falling over.
So is that kind of like an overcorrection of coming over the curve?
Part of it could be because of the overcorrection, but it could also be it's a combination of overcorrecting for the curve as well as just catching the inverted pendulum. Because the way I designed this is the way I designed that baseline controller, that K, is I prioritized make sure that that inverted pendulum is always balanced. So when it's flying, like that's why it doesn't follow the black line perfectly, because there's more priority on keeping that inverted pendulum upright.
Does the black line assume that the inverted pendulum will be upright at all times?
Yeah, so the black line assumes that everything is just a point mass. So in order to generate that, I assumed that the dynamics were just a point mass with some thrust. And then when I transfer it over, I was like, oh, it's some reasonable assumptions. The quad should not tip over too far. It should still follow our constraint, but that's something that you do have to analyze.
I had another question. When you hypothetically scale this up, what are some other constraints that you would have to take into account for as well?
Scale this up to like the physical system or a bigger, like an actual launch vehicle?
An actual launch vehicle.
Other constraints that you would have to account for.
So constraint, is the question, are there constraints on the quadcopter that you don't consider on the quadcopter that you have to consider on the spacecraft? Is that the
Right.
launch vehicle?
I don't remember off the top of my head.
Are you asking like atmospherics and stuff like that?
Yeah, I would just think that what are some other things that you have to think about when you actually implement this simulation onto an actual system that would go into higher altitudes?
I don't know, because I think there's some baseline assumptions as a controls engineer that like the vehicle can't do this. I don't know why, but I can't do this, or I'm guaranteed some performance of my vehicle, like another engineer that works in the like the propulsion systems can guarantee that I'll have this this performance of my vehicle. And so they kind of give the controls engineer, this is what your vehicle can do. And based on those, then the controls engineer can go through and figure out the trajectory. So the specific constraints, I'm sure there's a ton like this. A similar algorithm was used, well, a similar kind of trajectory optimization algorithm was used on the sky cranes that drop the Mars rovers. So when they drop the rover and they disconnect, they still have a lot of propellant and you want them to fly as far away from your rover as possible so it doesn't damage your rover. So it runs an algorithm very similar to this to get as far away as possible, and it'll just go and crash. So on an actual system, it really depends on your system, and there's all sorts of stuff that can go into it. But that's kind of the magic behind this, is like you can take whatever constraints you need and put them in here, and your solver, as long as everything is convex, will say, yes, I can find a solution, or no, I can't. And that's something that's very important for these algorithms, is you need to make sure that when something's flying, it's actually going to come up with a result. You don't want to plug something in and then your system's like, all right, I'm ready to land. And then it's like, oh, I can't find a solution. And so now you're just kind of not doing anything. So that's what something like this test bed can help with.
Thank you.
How much, if any, of your work has been informed by Falcon 9 booster landings?
Well, a lot of this work is motivated by it, or like at least this optimization stuff, that purple bullet has been very motivated. Actual like information from Falcon 9 and like SpaceX in general is proprietary, so I can't actually find like numbers and algorithms that they use. But this paper that I reference by Czech Meche, I think that's how you pronounce it. He worked with Lars Blackmore, who works for SpaceX and did a lot of stuff with that booster soft landing stuff. So this kind of algorithm, although I don't know exactly what's running on SpaceX, is potentially close to it.
At a later stage, when you use the test bed to apply to different like launch vehicles, would you have to resize certain parameters for the test bed, like the length pendulum and those kind of characteristics to match the poles of a certain launch vehicle, or is it sort of supposed to be a one size fits all?
Yeah, good question. We can change it. The way we've designed it is we can like unscrew the inverted pendulum and screw in a new one if we want to change the parameters to be like, for example, those aerodynamic forces, like some launch vehicles might want to tumble over faster than other ones. So we can adjust that based on those parameters. Right now, I think we're looking at just some numbers for the Saturn V and SLS for kind of sizing. Just like we're looking at frequencies and kind of determining what size of our parameters.
Yeah, so I find it very interesting. And I think about like balancing a stick on the tip of my finger, and then I have to also at the same time walk a particular trajectory while doing that. So there's two difficult things to do at once. Have you been able or tried to just balance the inverted pendulum like at rest without having to follow a particular trajectory?
As part of tuning this controller, like before I actually implemented this algorithm and like had it follow the trajectory, I did have a case where you just stay in place, like don't move and just make sure that you balance it. And so that was like step one. And then I was like, okay, now follow this trajectory.
But have you done that in practice with the actual quadcopter and an actual inverted pendulum to try to balance it?
No, we're still in the process of like getting the system flying. Because there's been a lot of work in just getting the quadcopter flying. And then like we have the hardware, but we're in the process of actually like getting flight tests. We have not flown the quadcopter with the inverted pendulum yet, but we are in the process, and I think within the next couple months we'll be very close to doing that, if not have already done that. Yeah, that does remind me that we actually, so if you go to our booth and talk to, I believe Milan is going to be there, he can talk to you about this mechanism that we have. So when we actually fly the quad, in order to get it off the ground, we want to make sure that the inverted pendulum doesn't move, because we just want to make sure the quad can get off the ground and not have to worry about balancing this pendulum. So we actually have a device that will squeeze, it's like an iris for like a camera. It'll like close and hold the inverted pendulum straight up while the quadcopter gets off the ground and we get things ready to run a flight test. And then we can flick a switch and that'll open up and the quadcopter will start balancing it. So the whole pointing constraint where we have to make sure that it doesn't turn too much is very relevant, because now we only have a limited window that the inverted pendulum can tip over before it's considered a failure. So like after 20 degrees or whatever that tipping angle is, it's like we consider that a failure of the experiment and close the iris and start the experiment over.
One more question. And we'll have to stop and move on to the next talk. Once.
Is the iris that you're using, is that the only option you were looking at, or is that just the best out of different options that you've discussed?
That was not the only option. There were other options that we looked at. I wasn't on the design team for that. That was Milan, what Milan worked on, and who will be manning the booth with our stuff. He can talk to you more about that. But once we found this idea, it was pretty, it checked a lot of boxes.
All right, let's thank Liam.